In this example, we're going to look at an AC circuit with, well, there's three branches in the circuit, but two of the branches contain a resistor and inductor, or resistor and capacitor, and we're going to analyze the circuit to calculate the current flowing in each of those two branches, and we're going to see how it relates to the voltage source that's driving them. So first, let me switch this into full screen so we can get a good look at the circuit. What we have on the left side here is an AC voltage source. So this is a sinusoidal voltage source. The voltage between the two terminals varies in the shape of a sinusoid. The amplitude of the variation, the RMS amplitude, is 230 volts. What that actually means is that the peak voltage will be root 2 times 230, and the voltage will go all the way down to minus root 2 times 230 as well. So there's actually a much bigger swing in voltage between the top and the bottom, and we'll see that in the simulation results here. Just to show you how I configured that voltage source, I've selected the sine option for the voltage source, and you can see that I've set the amplitude here to be 325.27. So it's not a coincidence that I've chosen this value. 230 volts RMS at 50 hertz is exactly the amplitude and frequency of the electrical power in Ireland. So I multiplied 230 by root 2 to actually get the peak amplitude, which is what you need to put in LTspice if you're configuring a voltage source in this way, and I've set the frequency to 50. I've also told it to generate 20 cycles of the waveform, which is going to be enough to cover the length of the simulation that I'm going to run. So that's the voltage source. We're going to be conducting a transient analysis. There are several other types of analysis you could use here to calculate, like DC operating point or whatever, but I'm just going to use the transient analysis, and we're going to expect to see possibly a little bit of a transient at the beginning before it settles into steady state behavior. The two branches then are just resistor and inductor, so it's a 100 millihenry inductor, and then resistor and capacitor, and I've got a 100 microfarad capacitor. So we're going to be doing a phasor analysis of this circuit in Octave/MATLAB. But first, let's just run the simulation in LTspice to see what we should be expecting to find when we do our calculation. So I'm going to click on the running man up here to run that simulation. Initially, no graphs are shown. We have to select what values we want to actually plot out here. So the first thing I'm going to look at is the supply voltage by clicking with the voltage probe on the top node in the circuit. And you can see there the sinusoidal voltage being produced by the voltage source. So remember that it's showing us the voltage between the two terminals of that voltage source, but the negative terminal is connected to ground, so the negative terminal is always at 0. So when we look at the voltage up here, we're seeing how the other terminal is varying relative to 0 or relative to ground. And it's going all the way up to 325 volts, and it's going all the way down to minus 325 volts. And this is exactly what the power line voltage does in Ireland. So we can zoom in a little bit on that sinusoid as well. If I just click and drag around part of the waveform, we can see it in a bit more detail. So there's our sinusoidal waveform, and we could pull out the cursor here as well, in order to just actually double check those peak voltages, for example. So you can see it's going up to 325 volts there, and if I drag it down to the trough, you can see it goes all the way down to minus 325 as well. So everything is basically as we would expect here. It's 50 hertz, so we are probably expecting to see a period of 20 milliseconds. That's 1/50th of a second. So if I add the second cursor on here and move that over to this trough here, we should be seeing a horizontal difference between the two cursors of approximately 20 milliseconds, and that looks about right there. So it's the horizontal difference between those two cursors that I've dragged on top of the waveform here. So we're basically ready to look at the current in the two branches here. So all I need to do to display those is to hover over them to display the current lamp, and I'll click on the inductor, and you can see that the inductor waveform is in blue, and then I will click on the capacitor and it produces the red waveform. Now it's important to emphasize that the red and blue waveforms here are currents, whereas the green waveform is the voltage source. So the green waveform has its vertical axis on the left hand side here. The red and blue waveforms, because their currents are referred to the scale on the right hand vertical axis here, which is in amps. And you can see it's going up to, I don't know, I think they're going close to like 7 point something amps and all the way down to minus 7 point something amps. So the current is oscillating back and forth in both of those branches. The major difference between the branches actually isn't the amplitude, because the amplitude is very similar of the current in the two branches. The difference is when they reach their peak. So you can see that the red waveform here, which is the capacitor voltage, it's the capacitor current, that reaches its peak earlier than the supply voltage, whereas the inductor current reaches its peak after the supply voltage has reached its peak. So there's a phase difference between these. That's the word we would use to describe it. And you can measure that in the form of radians. So there are 2 pi radians in one complete cycle of the waveform. But if there's some fraction of one cycle that a waveform lags behind our reference waveform here, we can express that in radians, or similarly, if it's ahead of it, we can express that in radians. And we're going to see that in our phasor calculation. So I'll leave this sitting here and I'm going to go and do this calculation using phasors in Octave. So let's switch over to Octave now. So I have Octave open here. I could type in commands just straight into the command window here, but I think it'd be more sensible, because there's going to be several steps in this calculation. It would be better to type it into an M file so that we can run the calculation more than once if we need to. So when I'm doing a phasor calculation in Octave or MATLAB, I almost always begin by defining what the frequency and the angular frequency are. So in order to do a phasor analysis, there has to be one fixed frequency in operation throughout the circuit. And in this circuit, it's 50 Hertz. So I'll just say F equals 50. And now the next thing we would normally want to calculate if we're working with phasors is the so-called angular frequency. So it represents the exact same thing as the frequency in Hertz, except that the units are different. So it's represented by the Greek letter lowercase omega. There is no omega key on my keyboard, so I'm just going to use W, which looks very similar to it, but this represents the Greek letter omega, so that's how I'll be referring to it. There are 2 pi radians in each 360 degree cycle. So if we have 50 cycles per second, the number of radians per second is going to be 2 times pi times that frequency 50. So this is going to turn out to be 314 roughly radians per second. So maybe I should put in some comments here. I just need to check what the character is for doing a comment here. Percent. Okay, so percent symbol is for a comment. So this one is angular frequency, and that is in units of radians per second. I'll just write that in full there. So the reason omega is so important here at the angular frequency is that when we have elements like inductances or capacitances, and we want to convert them into impedances to carry out a phasor analysis, the value of the impedance will depend on omega. So both inductors and capacitors respond very differently depending on the frequency of the current passing through them. So omega will be used in converting those element values into impedances. So we have a few different components here. We've got OR1, which, if I remember rightly, let's have a look back at our circuit here. So OR1 was 30. So that's 30 ohms. OR2 was 30 ohms as well. L was, I think it was 100 millihenries. Let's check it. Yeah, 100 millihenries and 100 microfarads. So L is 100, and then the way we notate powers of 10 is using the following notation. So 100 e minus 3 means 100 times 10 to the minus 3, so that's milli. 100 millihenries. And C is 100 microfarads, so that's 10 to the minus 6. This notation can be used not just in MATLAB and Octave, but also in C and C++ and lots of other programming languages. So it's very handy if you've got very big or very small numbers that you need to write in scientific notation, for example. This is a very convenient way to be able to do it. It saves you having to put in lots of zeros maybe after a decimal point or something like that. So this will produce much neater, more readable code. So to find my component values there, we're ready to calculate what the impedances of the inductor and the capacitor are. So the impedance of an inductor, this is something you'll learn a lot more about in upcoming lectures. You'll be covering the theory of this in a lot of detail. But for now, it's sufficient to know that the impedance of an inductor is equal to J, which is the square root of minus 1, the imaginary unit, times omega times L. So this is actually going to be an imaginary number because it's multiplied by J. So what that means is we're creating an impedance which has a magnitude. It's a complex number with some magnitude, but also with an angle of 90 degrees, which makes it purely imaginary. And all that really means is that the current and the voltage in an inductor are exactly 90 degrees out of phase with each other. That's what the angle of an impedance does. So if we build up some network of elements like resistors, inductors, capacitors, and we calculate the total impedance of that, it will tell us firstly how much it impedes or resists the flow of electricity in the same sort of way that a resistor would, but it also tells us how the angle of the current will relate to the angle of the voltage. So in this case, what this tells us is that the current and the voltage in a pure inductor are exactly 90 degrees out of phase with each other. The impedance of a capacitor is, which I'm going to just write using a variable named ZC here. We normally use Z to denote impedances. So in this case, I'm saying this is the impedance of the inductor and this is the impedance of the capacitor, ZC. So that's 1 over J omega C. So these are just formulae that you will learn off. As I say, the theory and the explanation for why these are what they are will be covered in lectures, but I'm not going to get into that here. It's just sufficient to know that these are the formulae for converting from an inductor, an inductance value in henries, into an impedance, which is an imaginary or complex number in ohms. This is the same formula for a capacitor. So a capacitance in farads converted into an impedance in ohms, which is in this case going to be imaginary. Okay, so that's ZL and ZC. So the good news is for the resistors, the impedance of a resistor, like Z or 1 for example, is just exactly equal to the resistance. So there's really no need for us to declare any extra variables, it's just the same number. So resistors, even in an AC circuit, they just have the exact same value as normal in ohms. So what can we say then? We've got, I suppose we can talk about the impedance of the first branch, which is going to be R1 plus L, because they're in series with each other. So R1 plus ZL. So if we look back at our circuit diagram for a moment, we'll see where we're looking at here. So there's R1 and it's in series with L. So we've represented L as an impedance. R is already basically the same thing that it would be as an impedance. And once we have two impedances in series, we can add them together, just like the way we would add like resistances together in a DC circuit. So here we're calculating the total impedance of that branch, Z1. So Z1 is going to end up being a complex number, meaning that it'll have magnitude, but it will also have an angle. The magnitude is going to tell us how much that branch is going to resist the flow of current through it, but the angle of the complex number will tell us what the phase angle will be between the voltage source and the current flowing through the branch. So that's Z1. If we wanted to calculate the current in that branch, let's call it I1. That's easy to calculate. We can just take our original voltage source, which I forgot to add in here, but let's put it in up at the top here. Vs is just going to be equal to 230. We're going to make this the reference phasor, which just means that it's going to have a zero phase angle. It's going to be a purely real number. Every other phasor in the system here, its angle, the angle of every other phasor will be measured relative to Vs, the reference phasor. So it's going to be a real number. The other phasors can be complex numbers, and the angles will tell us whether they're leading or lagging, ahead or behind of the reference phasor. So I1 is going to be equal to Vs divided by Z1. So this is basically just Ohm's law, but now I'm doing it with complex values. So I1 is going to be a complex number that represents a sinusoidal current. Vs is a phasor. It's our reference phasor. It represents the sinusoidal supply voltage. And Z1 is our complex valued impedance for the branch of the network with the resistor and the inductor. So that's the total voltage trying to push current through the branch. That's the impedance of the branch. And this is how much current actually ends up going through it. So it's Ohm's law, but with complex numbers. Let's do the same thing for the other branch. We've got Z2. It's just going to be equal to R2 plus the impedance of that capacitor, which is ZC. We can then calculate I2. It's just going to be equal to Vs divided by Z2, the total impedance of the branch. So that's I1 and I2, and that more or less gives us everything that we need, I think. So I'm going to save this. I'll just call it AC circuit.m. And if I switch to my command window, I should be able to just run that by typing AC circuit.m, or in fact just AC circuit without the .m. It will automatically append that. And you can see all of the steps in my calculation being carried out here. We've got the frequency being set, the angular frequency in radians per second, the reference phasor, which is the RMS value of the voltage source, that's 230. our two resistances, our inductance and our capacitance, calculate the impedances of the inductor and the capacitor, and then we calculate the branch impedances Z1 and Z2 and use those to calculate the branch currents I1 and I2. So really the most interesting thing that we get out at the end of this are these two complex numbers, I1 and I2. So these should give us a result that matches what we saw in LTspice. So I'm going to take I1 as an example. I1 is the inductor branch current. So in our LTspice simulation, that current was lagging behind the voltage source. In other words, it reached its peak later than the voltage source. So we're going to focus on I1 just for a second. And what I'm going to do is I'm going to add in some extra lines in here. So I'm going to say, what is the absolute value of I1? So that's going to tell us the magnitude of I1. Now that's going to be an RMS magnitude. So in order to get the peak magnitude, let's call this I1 RMS, is the absolute value of the phasor. So the magnitude of the phasor is the RMS magnitude of the sinusoidal waveform. So if I've got the RMS magnitude, I can then calculate the peak magnitude just by multiplying that by the square root of 2. So I'm creating a lot more variables than I need to here, but I just want to break this down into little steps. So that's I1, and we've calculated I1 peak, and then finally I just get I1 angle, or let's call it I1 phase. So this is going to be the phase angle of the current I1 through that first branch. So we can get the angle of a complex number in MATLAB or Octave just using the angle function, and in this case it's the angle of the actual phasor I1. So I1 here, remember, is a complex number. It has magnitude and it has an angle, or equivalently you can think of it as having a real and imaginary part. This gets the magnitude of the number I1. This gets the angle of that number. So there's sort of the two different values that are encoded into the one complex number. Okay, I need to save those changes. Then back to the command window and run it again, and you can see you've added on some extra bits here. So it's telling us that the peak in I1, the peak current is 7.4879 amps. Now if I compare that with what we got in LTspice, so I want to compare that to the blue waveform here. So I'm going to use the cursor to measure the peak value here. And it's very close, yeah, so it's 7.4. If I can position this exactly right, probably even get it a little bit closer. 7.45 is what I'm getting there. So that's the peak current in amps. And if I bring it down to the negative peak here, yeah, you can see it's minus 7.45-ish as well. So it's good agreement there between the calculated value from Octave or MATLAB and the simulated value here. Now what you can see there is that that inductor current is lagging behind. In other words, it reaches its peak later than the voltage source. So we would expect, because the voltage source is the reference phasor here, we would expect the phasor for the inductor current to have a positive phase angle, which means that it arrives later than the peak in the voltage source. So let's have a look at the angle there and see whether it did come out as a positive number. So I1 phase, sorry, excuse me, I have that the wrong way around. The phase angle is negative if the phasor is lagging behind. So I1 has got a negative phase, meaning that its peak arrives after the peak in the reference phasor, which is the voltage source in this case. So that's correct that we have a negative number there. Let's just finally add on the calculation for I2. So the RMS value of I2 again is just going to be the absolute value of the phasor. So the phasor, the complex number, is just I2. ABS gets the absolute value of that. That's the magnitude of it. So this gives us back a real number, and that is the RMS magnitude I2. To turn that into a peak value, just so we can compare it with the peak in LTspice, we just multiply that value by 2. So the normal convention is always with phasors that they are that the magnitude is the RMS magnitude, because it simplifies a lot of the power calculations when you're using phasors to calculate powers. So almost always phasors, the magnitude of a phasor will represent the RMS magnitude rather than the peak magnitude. But it's so easy to convert between the two. You just have to multiply or divide by square root of 2, but you do need to remember to do it, otherwise your numbers will be coming out wrong. Then finally I2 phase is equal to the angle of I2. So save my changes, go back to the command window and run the program again. So you can see everything from here down, that's the result of the program. And you can see that the values there for the peak, they look very similar to what we got in LTspice, because the magnitude of that capacitor branch, the magnitude of the current in the capacitor branch was very, very similar to the magnitude of the current in the inductor branch. However, the phase was totally different. So you can see here that the phase is a positive number, and it's even more positive than the other one was negative. So there's a huge difference in phase between them, which is exactly what we would expect for a capacitor and an inductor. So this is good. Basically, this is going to be the screenshot that you want to get. This screenshot here with the output of the program here, just showing exactly what I'm showing here. Then you'll know you've got it right. So I'm going to actually screenshot this. So I use the snipping tool. Can I use that? Now I'm going to use, let's use this. So just do the active window. Hopefully that'll capture it. Yeah, so we'll upload that to the instructions now shortly. Just before ending the video, let's just have a look back again at these waveforms here. So one way of thinking about why the inductor and capacitor values have this opposite behavior in terms of their phase is, in order for the capacitor to build up its voltage, like current needs to flow into it in order to create the voltage difference between the plates, because they need to be charged up. So in a way, the current, you can think of the current in the capacitor causing the voltage to build up on the plates. So the current has to come first, really, and that's why the capacitor current is happening here before the supply voltage actually reaches its maximum. The capacitor current has already peaked. Conversely, for the inductor, in order to change the current in an inductor, you have to do work. So you have to apply some voltage to the inductor to change the current. So as a result, the voltage has to be present first in order for the current to change. So therefore, maybe it's not surprising that the current in the inductor is lagging behind the voltage that's being applied to it. So that's why the capacitor current is going to be leading and the inductor current is going to be lagging, or in other words, happening later. So in terms of phase angle, that means there's a positive phase angle here and there's a negative phase angle here. So I think I'll leave it there for that video.